Swayam Prabha. Digital India. Educated India.
Welcome to week 5, lecture 2 of our NPTEL course on Muffler Acoustics. Before we begin this week, let us very briefly review what we intended to do in this lecture 2, that is the things that we discussed back in lecture 1 of week 5. So, basically we just stopped at the analysis of the transmission loss of extended inlet and outlet element. If you recall, what we basically did was that we actually considered in detail the transmission loss properties, that is the characteristic features of the transmission loss of a simple expansion chamber muffler. So, this was the simple expansion chamber muffler, and we saw that, I mean, after a little bit lengthy derivation, we saw that the transmission loss of such a system then is given by the following expression, which is of course we studied that in detail. So, this is given by your 10 log to the base 10 plus 1 plus 1 by 4 1 m minus 1 by m whole square into sine square k naught L, where m is your square of your diameter ratio. M is nothing but d naught by d square, and you get periodic domes and trough. These are called troughs, these are called domes, and we studied in quite a bit of a detail that why are we getting all this and some simple approximations and all that. So, it turns out that we do get these domes and troughs, that which was mentioned somewhere here. We get these domes somewhere here at certain frequencies. If you recall, those, what were those frequencies? K naught L is equal to pi by 2 or 3 pi by 2, 5 pi by 2 and so on. So, we could basically readily work out what were those frequencies. I have not going to derive that again, I will just probably mention it. So, those were the frequencies given by 3 C naught by 4 L, 5 C naught by 4 L, and of course, the first frequency is C naught by 4 L, that is your C naught by 4 L. We get all these things where we get the maximum transmission loss, and on the other hand, when this thing is there, we get 0 transmission loss. Now, just when we stopped at the last lecture, we figured out that there could be a smart way to eliminate these problematic areas, you know, the ones that I am sort of circling. Let me draw it cleanly, let me draw it rather cleanly for you. So, this was our thing, isn't it, and these were the problematic areas, isn't it. So, our focus was then how to resolve, how to completely kind of kill those troughs. Is it possible somehow to do that? Well, it turns out that there is indeed a smart way to kill these troughs, that is by, if you consider a structure or a configuration like this, instead of a simple expansion chamber with flush mounted tubes, if we consider this kind of a thing. So, what does it do? How is this different from, perhaps let me just get rid of this part, how is this different from this? Let us try to understand the theory underlying this completely in this lecture. So, the length L remains the same, and the only difference that we have is that the pipes are inserted into the chamber in the configuration. Well, let me say this is configuration 2 and this is configuration 1. So, such a chamber in which the inlet and outlet ports are kind of protruded or extended inside the chamber with a view to generate peaks at certain frequencies, such that it is coincident with the natural frequencies of the chamber, overall chamber. and when it so happens, then the troughs are uplifted, the troughs are cancelled by the attenuation peaks, and then you get a much better transmission loss performance. Overall, the transmission loss performance would enhance. So, let us understand the maths underlying it. Suppose we do not know what would be the length, we assume arbitrarily the length is L1 of this extension and L2 of the outlet, the port that is also outlet port that is also extended inside the chamber. So, this is the inlet, this is the outlet, and when you have this extensions, you got certain things like this, then it is possible that we can create resonances by suitable insertion by tuning the lengths. Now, all this while we are assuming only planar waves to propagate, that is here the planar waves propagate, and here also in the chamber there is plane wave. So, when the acoustic wave is incident just at the interface of the extended inlet and the chamber, a part of that is going or is diverted towards the annular cavity and part of that is going here. So, but before that let's figure out the resonance that the waves sees right at this section marked in yellow color. What is the impedance? So, remember this is a quarter wave resonator. So, essentially what we have is a cavity, is an annular cavity, so we are trying to figure out the resonance frequencies of this cavity. So, with this in mind, let us say y naught is your C naught by S chamber and inlet and outlet diameters are assumed to be the same. So, y p is nothing but C naught by S p. So, what is the characteristic of frequency of the annular cavity? It is C naught by divided by S c minus S p. So, we will keep these relations aside, that is to say if you have extensions like this. So, what is the characteristic impedance of this annular section? Okay. So, what is the characteristic impedance? We know this now. Let us figure out what is the impedance that is seen by the wave when it is just incident here, that is looking into the cavity of length L1. It is minus j y n into cot k naught L1. That is the impedance that is seen by the wave when it is incident right at the interface. So, now let us say P tilde and by U tilde is equal to Z1 times this. So, let us introduce some nomenclature or naming the point. So, this is 1, let us say the point just outside the interface is 2 and this is 3. So, this is then P 3 tilde by volume velocity or mass velocity V 3 tilde. So, that is Z1 is equal to minus j y and into cot k naught L1. Okay. What do we do with this particular expression? How do you use that? So, remember, if you recall our last lectures, if we had a certain tube such that it was closed at one end and there was a wave coming here. So, if you could tune the length L1 such that most of the acoustic power is diverted in the side branch and very little or negligible power is transmitted downstream, then you can significantly abate or control the noise or the sound that is propagated downstream, at least in that frequencies or for tonal frequencies. And it turns out in this case it is going to significantly not only kill that particular trough or that problematic frequency, it is overall going to improve the transmission loss performance in the vicinity of such a problematic frequency. So, when is the impedance Z1 of the annular cavity going to 0? When is that going to happen? I should have probably named it as Z and 1, annular cavity 1, because there is annular cavity 2 also at the extended outlet. So, when this term is going to 0, that is cot k naught L1 is equal to 0, implies cos k naught L1 is equal to cos of pi by 2, then the impedance Z1 is 0. So, what does this mean? It basically leads us to the familiar thing. Actually, this in a more general sense can be written like this, where n is equal to 0, 1, 2 and so on. So, this is pi by 2. So, what it means is 2 pi f into L1 by C naught into this to L1. So, let us start cancelling terms. Pi is cancelled, and f into L1 by C naught is equal to 2 n plus 1 by 4 here, and you can multiply both sides by C naught to get rid of the denominator, and f, let us say this is peak f p, and let us divide this by L1 further to get this. So, f p is equal to 2 n plus 1 into C naught by 4 L1. So, that is what we are going to get. Now, let us look at the lowest possible frequency. This expression I am sure you would have come across. So, n is equal to 0, this would give us C naught by 4 L1, is not it? And let us recall from our last lecture, what is the trough frequency, what is going to happen to the frequency of the trough when you have a chamber of length L. So, let us go back to our last slide. So, here we were. So, when L1 and L, so so naturally the trough will happen. Let us recall the last discussion. So, this was what we had, C naught by L, I am not sure why this was there. So, C naught by L is the first frequency, first axial resonance frequency. So, going back to our slide here, so f trough is equal to C naught by 2L. This is the frequency at which the first trough occurs. Now, if we were to somehow choose the length in such a manner that f p is exactly equal to the f trough, that is the frequency of occurrence of the peak due to the quarter wave resonator, that is when the frequency at which the impedance of the annular cavity is tending to 0 is exactly equal to the frequency of occurrence of the trough of, or the first natural frequency of the chamber, then you have the following condition. So, let us start cancelling the terms and simplifying. So, L1, it turns out it is nothing but L by 2. Why? Because of course, this cancels, you get this, and simple algebra would basically get you the following. L1 is equal to length by 2. That is to say, if you have a chamber like this, and this is L. So, L1 is equal to L by 2. So, basically if, in other words, if you were to choose the extension in such a manner that it is half the length of the chamber. So, half of the length. So, basically you need to insert the pipe for almost half the length, not almost, exactly half the length of the chamber based on the one dimensional or planar wave propagation, then you can in principle eliminate the trough. Now, we can actually do the similar exercise for the annular cavity at the outlet, that is the cavity that is formed here. So, how do we go about doing it? So, Z and 2 is minus j and 2 into cot of k naught L2. So, when similarly if you have, one needs to find out really the frequency where which the annular cavity resonance occur. So, this we need to find out f p. So, for that we again set this term to 0 to finally obtain k naught into L by 2 is equal to 2 n plus 1 into pi by 2, is not it? So, when you get such a thing, so what is the first frequency? Of course, looking at this formula, it is easy to figure out that f p for the cavity at the outlet is equal to C naught by 4 L 2. So, this was L 1, let us say this is L 2, this is L 2. So, when you have this kind of a thing, then when you have basically this expression, this frequency for a certain L 2, for the first axial resonance frequency, at which the peak will occur for the annular cavity at the outlet is given by C naught by 4 L 2. So, let us try to eliminate the second trough, that is the second natural frequency. So, if you recall our last the slides, these ones, this was the first axial resonance and this occurred at C naught by 2 L. We should be able to, we will do some MATLAB simulations and which we will show that if you have L by 2, this trough is completely eliminated by the peak here, and for eliminating the trough due to the second axial resonance, that is C naught by L, one has to basically equate the second resonance frequency of the chamber with the axial resonance, with the resonance frequency of the cavity formed at the outlet. To do that, this must then be equal to C naught by L. All right. So, let's simplify these terms. So, you get C naught by 4 L 2 is equal to C naught by L. You get these terms then are cancelled, and what essentially we get is L by 2 is equal to L by 4. So, these then are the relations, is not it? And so, we have two relations, L 1 is equal to L by 2 and L 2 is equal to L by 4. So, basically the idea is very simple then, how to tune the performance, and we will soon see some transfer matrix derivations for this extended inlet element, and we will see some MATLAB or Maple based simplifications in a while. So, basically what really one needs to do if we go by the planar wave or axial plane wave propagation approach is that the idea is to simply not just flush mount the inlet and outlet pipes, we have to basically insert it by length L by 2 and L by 4. So, if we are able to accomplish this, if we are able to get a configuration made such that the inlet is extended by half the length of the into the chamber equal to the extension length being half of the chamber. Similarly, and the outlet is extended into the chamber with extension being quarter of the length, then the first and second axial resonance frequencies can be eliminated. We hope that, and we will show that. But there is one more thing that I would like to point out, that let us say we consider the extension length L 1 is equal to L by 2. So, let us see how we are able to in fact use the extension length L by 2 to also possibly eliminate higher order troughs. So, now if we recall our expression for the impedance for the annular cavity 1, we have minus j y and 1 into cot of k naught into L 1, but we already chose L 1 to be L by 2. So, we get this, and let us also recall the troughs of the chamber, that is the resonance frequency of the chamber, are C naught by 2 L, C naught by L, C naught by 3 by 2 C naught L, and 2 C naught by L, and so on. So, now let us say, so these are the things. Now, hopefully we have already taken care of this and this. How do we ensure that just by choosing L by 2, this would possibly kill the higher order troughs as well? So, if we choose Fp or the frequency k naught corresponding to this frequency that is 3 by 2 into C naught by L. So, what do we get? K naught for such a case will be 2 pi into F by C naught, and your 2 pi into 3 C naught by 2 L by C naught. So, let us start cancelling the terms. C naught is cancelled, 2 pi is cancelled, and is equal to pi by L, is equal to pi by L. Okay. So, this is what we are going to get for K naught. Now, let us use another slide. An annular cavity 1 at such a frequency is nothing but j, y and into cot of pi by L, because K naught, remember this was pi by L here, and into L by 2 multiplied by L by 2, and here it was pi by L. So, we cancel this and we get minus j y annular 1 into cot of pi by 2, which is nothing but 0. So, what does it mean? It means that we can also hopefully take care of this frequency. Why? Because the trough occurs at 3 C naught by 2L, the third one, that is in the sequence of troughs, I guess, which I presented somewhere here. This one, this will again go. So, this one 3 C naught by 2L frequency, this was the frequency axis, this was the transmission loss. So, hopefully we should be able to take care of this as well. But how far we can go with L by 2? So, L by 2 is actually, we anticipate that because the trough, axial resonance trough here and the peak, the frequencies are mutually coincident. So, the peak would hopefully cancel out the trough, the first one as well as the third one, that is here. So, we would get something like this and something like this. We will soon see, we will get the transfer matrices derived and show some results in MATLAB based on the planar wave theory. And then the whole idea behind is to extend the broadband or extend the attenuation performance for as high frequency range as possible. Because remember, let me reiterate here, I have done so in the previous classes, that apart from the automobile or the engine exhaust system is really a variable, is a device which produces noise sources at different frequencies based on the running speed. So, ideally we would want to have a resonator that works well for a broadband or as wide range of frequencies as possible. So, we would want in general to have a broadband attenuation and plus good low back pressure drop and pressure drop or things like that. But so, just by L by 2 extension we are able to take care of this one and this one. Can we go for higher order troughs, that is 5 C naught by 2L? Is it possible? So, let us see if that is the case, because your other higher order frequencies would probably occur at, this occurs at 3 C naught this thing. So, this would probably occur at 5 C naught by 2L and so on. So, if you have such a thing 5 C naught by 2L and 2 into pi by C naught, 2 pi f by C naught. So, C naught obviously is cancelled and 2 is gone. Then the term that you have on this side is L by 2. So, basically what happens is that L is cancelled and you get 5 pi by 2, 5 pi by 2 you are going to get. So, obviously when you do the cot of this, cot of 5 pi by 2, so that is cos of this argument by sine of this argument. So, this will also tend to 0. That means theoretically if you take L by 2, it is going to eliminate even higher order troughs, that is 5 by 2, 5 divided by 2 into pi and so on. But then we probably should not celebrate a bit too early, because there might be some problem when you choose L by 4. So, for this one we know that when you choose L by 4 it is going to cancel out the second trough, but can it cancel out the fourth trough, because the fourth trough would basically correspond to the frequencies given by. So, here we were basically here we would get 2 C naught by L, 5 by 2 L into C naught and so on. So, by choosing the outlet length to be L by 4, we could get rid of, we could match the resonance frequency with the second axial resonance, and now the job is really to see whether we are able to match the two second or the fourth resonance frequencies, because remember 5 C naught by 2L is the fifth axial resonance frequencies, and by choosing L by 2 we can possibly kill out or eliminate this trough. But before we get too happy about this thing, it is very important to check whether by choosing L by 4 we can cancel out 2 C naught by L, that trough, the trough corresponding to that, because that occurs earlier than the fifth one, the fifth axial resonance frequency, and we can't change L by 4 because you have really you would want to eliminate the second trough, that is your priority. And again, because engine noise is concentrated at the first firing frequency of the cylinder as well as its first few harmonics. So, the lower frequencies are of always a priority, and unfortunately most mufflers, at least the reactive mufflers, they don't seem to give a very good performance in very low frequencies, unless you of course increase the expansion chamber area expansion ratio. Anyhow, let us get back to our discussion. Let us put the frequency as 2 C naught by L in our slides, that in our ensuing slides. So, I will get rid of this part, and put 2 C naught by L into 2 pi by 2 pi f by C naught into L by 4. So, we cancel this part, and we are left with this multiplied by this. So, this is cancelled, this is cancelled. So, this becomes 4 pi by 4. So, we get pi. So, then what is the argument of the annular cavity? A and 2 is equal to minus j and 2 into cot of pi, which is definitely not 0, it is actually cos by sine, right, cos pi by sine pi. So, it is actually tending to infinity theoretically. So, that means if you have a resonator with length, so if this length is your L by 2 and this is your L by 4. So, what would happen then? It would kill the first axial peak, axial resonance, second axial resonance due to this, the third one as well, but fourth one it is not going to, it cannot eliminate the fourth trough. This for the simple reason, because the impedance based on the plane wave consideration, the impedance seen by the plane wave at this section at frequency given by 2 C naught by L, at this frequency the wave sees here infinite impedance, or it tends to basically completely transmit the acoustic power by following the least path of least resistance or least impedance, and it goes directly in the downstream. So, let us draw things afresh, let us draw it afresh. This was something like, let me draw the simple expansion chamber thing with a blue curve, 3, 4, 5 and so on. So, pi, 2 pi, 3 pi, 4 pi, these are all non-dimensional frequencies. So, we can actually name this as k naught into L, and here if you have transmission loss, that is dB. So, what will we get? We will get, when you choose of course something like this, when you choose something like this, L by 2 and L by 4, let me make it more this thing. So, then we are possibly going to get things like, it is going to kill the third trough as well, and here it is going to break down. It might increase at this thing, but then increase here is probably inconsequential because you already have a dip here at the fourth this thing. So, basically the first, by choosing, so what is the moral or the take home message of this lecture? That based on the plane wave propagation theory, plane wave propagation, if we choose our length of inlet pipe to be extended into the chamber by L by 2 and outlet pipe to be extended into the chamber by L by 4, we can get rid of the first 3 troughs. That is important, and of course, assuming here waves are planar, and these are all quarter wave resonators QW1, QW2. We probably, by this simple trick, we can possibly extend the broadband transmission loss range a lot. We can definitely improve the transmission loss performance. It not only, we will see all these graphs for typical configurations using a MATLAB code, and maybe some simplifications using Maple algorithms, Maple Maple worksheet, and we can derive the transfer matrix of the entire thing right from the point here. Let us say this is the point 1 and this is the point 2. We can derive the transfer matrix between these 2 points, and we can see all these things wonderfully happening, and then worry about basically simplifying things and plotting it and all those kind of things. So, that will be the focus of our next lecture, and till that time stay tuned, and I will see you in the next lecture. Thanks.